Good morning, everyone. Fantastic. Thank you for the invite, by the way, to talk to you. You might not thank them for letting me loose talking to you, but hey, there we go. Thank you for the invite to talk to you. This fantastic place. And also that first introduction has kind of left me in a way, a bit speechless, because it said everything I was going to say, in a way. So I guess what I might do is validate, because I'm a Rolls Royce engineer and we love validating and verifying and proving things work. Validate some of the things that were said by talking to you about where I work. So I joined Rolls Royce in 1990. I look after engineering methods now. I work for a chap called Chris Young, who's our group chief engineer. He reports to our chief technology officer. And I'm accountable for looking after our engineering method strategy and how we go through a journey of equipping our engineers to be successful in developing products. And I find that a fascinating place to arrive. It's not where I started, because I'm not a methodology person. And the last bit of software I wrote, I will now confess, was a university in COBOL as part of my third year studies. That was the last bit of software I wrote, unless you count Visual Basic macros in Excel. The mother of all, the mother lode, the basis of low-code stuff, you might argue. Certainly in our businesses, people have been doing it for years with Excel spreadsheets. And so I joined Rolls Royce in 1990, and there were still drawing boards. Right, we drew every component by hand, on film. Some of the older engines, I am assured, we actually had printed on vellum for preservation reasons. That's how the place worked. It was drawing offices, there was hundreds of people in them, we drew every component by hand. We had some computers. If you were lucky, you could book a PC and take your desk up and go and try and use Power Project and things, and we had plotters to print your charts. But presentations would be putting slides on an overhead projector, which I was astounded to discover in my son's school the other day. So there are still a few around, but slides are on overhead projectors. Some of the younger members of the audience will be now completely baffled as to what I'm on about. But you put this thing on a screen and it would project its image by the laws of physics and manipulating light. And that's what the world was like when I joined it. And the products we were designing was actually a bit like these cars. If I go over to that Red Bull number 1, it's a bit angular, isn't it? It's a bit square. Right? And the products we were designing were frankly angular and square. They performed incredibly well. The Pegasus jet engine that powers the Harrier, and the RTM322 that powered helicopters, and the original RB211 that went on Boeing 747 and the TriStar. If you actually take them to bits and you look at the parts, there are some aerofoil shapes, but they're all two-dimensional. They're stacked two-dimensional shapes. And a lot of the parts are tubes, so cylinders, they're square. They're not three-dimensional aerodynamics, they're not four-dimensional aerodynamics at all. I found it fascinating walking around here this morning with one of my colleagues. We ended up at the 21 car. And if you actually go and look closely at it, at all the fins and shark fins and looking at the underside, the side trays of it, the front nose, the front wing, they're an incredible example of three-dimensional, four-dimensional aerodynamics. You can only do that if your CFD and CAD are tightly coupled, and they're tightly coupled to a manufacturing process that can cope with those shapes and the quality constraints in those shapes. Same in a jet engine. The inside of a turbine blade, right, is a bit cleverer than that, but it looks like that. It's full of little shapes, it's full of turbulators, it's full of things to control the flow, and we're manipulating where the air is going through the inside of a turbine blade to make it efficient and survive at 200 or 300 degrees above its melting point for thousands of hours. And we do it by tightly coupling CFD, mechanical, thermal, CAD, manufacturing all together. So it's essential for us as a business. We are an IT-intense, an IT-heavy business. And we've got pictures like this I could draw in the mid-1990s with some of the strategy papers that I've got back in the filing cabinet. We've got a completely end-to-end process and toolset. Everything is joined up. We go from talking to customers through requirement documents, through Polarian and doors and things like that. We have functional modeling that's done with bespoke bits of Fortran code, as well as toolkits you can buy, like Cameo, Capella, SysML tools, Modelon, etc. We model completely on CAD. We control product structures completely in a PLM instance. We feed it into manufacturing processes that are completely automated. We write machining tapes. We write machining programs to mill the parts. We have automated programs to control how foundries work, how parts are inflated in hot forming dies to make fan blades, how we lay tapes up to make composite parts. all automated and driven through a production organization, out to the customer. When we give it to the customer, we're responsible for it for 50 years. Every product we make, we have to maintain an ability to recreate what we did in it for the life of type plus 10 years after the end of production, is the typical aerospace rule. So we've got a complete understanding of what our customers are doing to our products. We have edge computing. Every engine has got sensors on it, and they stream data back to us. Some of that's in real time, some of that's periodic downloads, but we know exactly what every customer is doing to every product, providing we've got the right deal with them and the right contract in place. Some customers don't like to tell us. Most customers do, because there's an advantage to them. We use that data with them to optimize the way they use the asset. We can tell an airline if a pilot's not being gentle enough. We can tell an airline if it's using the wrong kind of fuel. We can tell an airline if it's flying too many cycles and it's wearing the product out too quickly. We can optimize the way the airline extracts value from the asset that it's bought from us. We can move to a territory where we can own the asset and we can just deliver thrust. Because we can manage all the variables of that device being used in a very complex environment, a very variable environment, and we can do it because all of this is joined up. But building that's taken us 30 years. So I was absolutely fascinated about Tom's chart about how hard it is to write applications and do enterprise IT, and there's at least one colleague in here, who I won't name, but he knows who he is, who worked with me in Rolls Royce doing this kind of stuff for a few years. And it's incredibly hard to deliver an integrated environment and maintain it when the technology basis that it's built with and the technology it's being applied to is radically transforming. So I'm having a fantastic time running the engineering methods and CAD and the PLM team. I can just about cope with doing two-dimensional CFD on a CAD model and maintaining the configuration by about 2010. Unfortunately, at that point, I'm putting 3D aerodynamics in. I just observed to one of my colleagues, that car is a fantastic instance of three-dimensional aerodynamics. I was putting that on Trent 900 fan blade in 2002-ish. The same basic technology. So that's not me being arrogant about Rolls. The product had to do it in order to deliver the performance the customer wanted. But the technology base, the information systems couldn't cope. And so what we found was the engineers would make it cope. They would write stuff. And our original low-code, no-code platform was actually the mainframe that our configuration management system now sits upon now. But we used to run everything off of a mainframe. So we had a computing block in Derby. We had one in Bristol. It had mainframe compute in it. People would log on a green screen and they would type in their command lines. They'd write Unix, they'd write Fortran, they'd race it through compilers. We'd have a management system to control it. And it was distributed through all the engineering teams. So we had little pockets of method developers dotted around all the engineering departments writing all these codes. This was in the 1990s into the noughties. But we found that they all wrote them differently. And they all documented them differently. And they all released them at different points in the life cycle compared to everyone else. So we started to grow like higgledy-piggledy, a whole morass of software around this swoosh. And I've even got into talking about how we interact with the green stuff at the bottom when we talk to the SAP tools, the enterprise resource planning tools, and the manufacturing tools, and our suppliers. And doing that's quite hard, so that's where the Visual Basic kicks in. We find people writing spreadsheets and then automating them with scripts to manage transactions between the blue and the green, because it's too hard to get the enterprise systems to join up. So all that stuff that was talked about, the gap between demand and supply with creating software and keeping pace, absolutely true. And I know I've got some colleagues from British Aerospace who are going to talk later, and I would imagine they've found similar stuff. Because the technology pace of our industry is totally different to the technology pace of our IT department, and that's totally different to the technology pace of the IT industry. So moving around that shape, from 60,000 feet, it's dead easy to go around that landscape. I can describe it. Oh, we put it in PLM, we put it in MES, we feed it to SAP, we execute the order. It's really simple at a high level. But when you go and actually look for 200 feet height, it's a horribly complicated situation, full of all sorts of software and bespoke code that's been written, full of all sorts of fudge factors, full of people bridging gaps and hoping that they're doing it the right way. Because although you've got a process document that says how they should do it, it doesn't really say how it's done, because that would be too complicated to write down. So we're very reliant on people. Now that's good, Because people can make some great decisions and react to some difficult situations much better than an artificial intelligence will ever do. But it's terribly unproductive when things are running normally. So what we used to do, and what we still do to a degree, is we try and cope with an IT portfolio. So we've got business demand, and we've got IT teams. Some of those teams are centralized and service a group. Some of them are based in our individual business, like the civil business or the defense business, or our growing electrical business. And they have authority to construct portfolios of investment like this, and we buy Team Center 12, and we look at refreshing our SAP, and we buy Microsoft products, and we do deals to lease clouds or access cloud space, like on Azure. We equip our shop floor with standardized templates for things like Ops Center, for example, or other products in other sectors, depending on what our PLM system is. We buy test beds and we equip them with software to test our engines. Some of that we have to construct ourselves because you can't buy it. So our test execution system is homegrown because we couldn't buy anything when we needed a system that would do what we wanted. We think we could just about do it now with some off-the-shelf products, and we might move in the future. And we put it all in an infrastructure. Infrastructure is another interesting conundrum for us, another interesting conundrum for the low-code world. Because our infrastructure is fundamentally hobbled by a couple of things. The first one is the amount of data we create is growing exponentially, and it's already a scary amount. When I make a part, I can create gigabytes of manufacturing data for one serial number of a part, and I've got to put it somewhere. But I can't put it on the cloud. I can't just go straight to a public cloud and put it on there because most of my technology is export controlled. It's got intellectual property in it that's precious to me, and it's covered by government regulation for the export of goods, be it dual use, so potentially it's something that could be used for a weapon, or it's got a military rating. And even if it hasn't got any of that, I still need to rate it as not having any of that. So I can't have any data that I don't know what it is, which means I need to build an infrastructure that can cope with that problem. And guess what? That's quite hard to do because all the big vendors have slightly different approaches to managing it, and the regulations from governments are all different. So I've now got a melange of situations to cope with. I've got more use cases than an investment portfolio can cope with. So I need to equip people at a working level to deal with that problem. I need to equip them with the ability to write software that's compliant. And that's quite hard in my industry, particularly if you've got all the things that were being hinted at in the previous presentation around your neck. You don't have enough developers, you don't have a good environment for them to work in. They don't really quite know why they're doing it because the signal between the customer and the supplier of the system is a bit tangled. So our people try desperately to cope with that. And we need to break that problem down. We need to stop it. We need to sort it. Because we can't create software fast enough to cope with how we want that picture to evolve. We can't create integrated business systems fast enough to cope with how we want that picture to evolve. And if we can't do that, we can't deliver what our customers expect. We can't deliver the services they expect from us. We can't deliver the technology leaps they expect from us. So we have to find a way to break this paradigm about IT project delivery. I promised myself I wouldn't use the word paradigm, and I went and did it. I do apologise for that slip into consultant speak. I'm not honest. And probably the magic, the route we have to take to do that is the land of no-code, low-code, Mendix. And I'm not saying that because I'm a fan of Mendix, because I don't know yet. We've not really started using it. We've only just really started picking up and putting it in our state. We're having a few goes at using it in some very interesting applications, which I'm not allowed to tell you about, some of them. Some of them I can. We're doing it for some dull stuff like managing data sets to do with safety and security. We're doing it for some incredible stuff like automating system design for jet engines, which is a real holy grail in terms of improving product development, timescales and performance and productivity. So we want to roll these kind of toolkits out to our people because we need to break all those problems that were described in the previous presentation. We need to enable far more of our employees, of my colleagues, to safely construct toolkits without me having to worry about putting them into these big buckets to get IT to do it for them, because the infrastructure and the setup that we've been operating on is too clunky to dare let them loose with changing it. We have to try and move away from that. And so one of the ways we're thinking about it is kind of all crammed onto this terribly busy chart. So the green is our citizen coders, our engineer. We want our engineers to feel comfortable about being citizen coders in the modern vernacular, because we've always been quite comfortable with that idea, just not quite able to fully let go and let them have the freedom to do it without too much supervision. But we've always been quite comfortable with the idea of engineers coding in our company. We've got massive sources of data. Production, I just said, per part, gigabytes of data per part. A jet engine's got 30,000 pieces in it. There are about 500 of them that are truly significant. We make an engine. Pre-COVID, we were heading towards making an engine a day on 2 to 3 sites. Now, COVID has cut that demand back quite significantly because our customers stopped flying. The demand will come back. Whether it will come back as the jet engines we've got today or something more novel, the jury's out on that, but it will come back because the world wants to fly. So production data, lots of it, and we have to keep it for a long time, and it's riddled with security and intellectual property issues within it, so we have to keep it safely and securely. And we can't keep it in the factory. We'll talk about that again in a minute, but there's no point in leaving it locked in the factory because I can't make use of it. Product data, we use PLM systems, we have Teamcenter. We have some interesting foibles in our current setup because although the product is designed in Teamcenter, the CAD models are associated to Teamcenter. The executive configuration management system is called CODAC. If anyone here has ever worked with NASA, they might recognize the acronym CODAC because it's the 1960s configuration management tool designed to make Saturn rockets and stuff. And we bought it in the 70s along with our first computer. And we've used it ever since as our master repository for configuration, because it holds all the information we need to bridge to our SAP system to make that green stripe work on the bottom of the first chart. So we're just about to go through a phase of trying to break that dependency upon that old piece of mainframe code. Even though it doesn't run on the old mainframe anymore, it's often a data center and it's wonderful and it's backed up. Some of the hardware I think they still buy from eBay, which makes me a little bit nervous. But we have to get off of using that mainframe code. And that means getting away from those bridges, which means, guess what? More citizen coding. Because we won't find all the use cases fast enough to do the IT investment quick enough to sort the problem out. Our assembly plants assemble the 30,000 parts to make a jet engine, one of them every day. Here's the funny thing, we need to keep track of virtually every assembly step on making a jet engine. Every nut, every bolt, every washer that's used, every torque that's set, every pipe that's fitted, we need to keep track of what was fitted, who it was fitted by, when it was fitted, how it was fitted. So our assembly plants are a masterpiece of craft-level skill and craft-level record keeping applied to a slowly flowing production line. So it isn't like, I remember going to see a Toyota plant once, and it was absolutely fascinating to watch these, and Jaguar as well, cars rattling along the line and people doing stuff. But I was completely back, well, why aren't they going back to the screen to put the confirmation that they've done it? Well, they don't need to. Why? Because the line drives quality. By doing the steps you're assigned to do in this part of the line, which you have to do, because if you don't, you're going to have bits left behind, the quality of the product's assured. The tooling makes sure it's done right. I can't do that for my products. I can engineer them in a way that makes them really foolproof to assemble, and I can keep track of stuff with intelligent tooling, but I've still got to say I've done it. It's a regulatory requirement. So our assembly data generates lots of little bits of information associated to every product. Not massive files, but lots of little pieces of information we need to keep track of. Test beds and simulations. Simulations, we can simulate what happens to a jet engine if I break massive bits of it at full power on takeoff. So there's a test criteria called fan blade off. You have to prove that the blades at the very front of a jet engine, if they fail, they won't come out the side, they'll be contained within the engine because they're an incredibly high energy piece of debris. They will go at hundreds of miles an hour through the fuselage. If you throw one of those bits, as we've done in the past, one of our peers has done, if you throw some bits of jet engine that are spinning around at 30,000 feet, they'll land several hundred miles away. So there's an awful lot of energy locked up in an engine, and we have to simulate that. We can simulate how that engine behaves in a fan blade off for 2 seconds of the cycle. It takes us 9 to 12 months to build the model. It takes a month to run it, last time we did it. So we've got massive simulation at one end of the spectrum. But virtually every part in the engine has been through CFD, finite element, possibly some vibration analysis, aeroelastic analysis, Quite a few of them go through manufacturing process modeling. So we generate vast amounts of simulation data that we have to associate to our bill of material. A lot of that's done with, guess what? Bespoke bits of code, bridging, local stores, local servers, tied to the individual that did it, not tied to the engine itself. So my data management question around simulation is terribly difficult. And then I've got testbed data. I've got about 70 years worth of jet engine testbed data lurking on my IT estate. I'm still flowing some of it to that mainframe construct. Every time I run an engine, we just built a testbed in Derby. Our latest testbed is testbed 80. If you're ever in Derby and you drive along Wilmore Road, you will see a great big concrete U-shape, because there's an exhaust at one end and an inlet at the other, and the bit in the middle is where the engine runs. And it's a big bit of kit. The working area of a testbed is about the size, if we turn this room on its side, it's about the size of this room. Generates about 12 gigabytes a day when it's running. That data has to go somewhere. So it goes on to storage on site, and then it goes on to storage on our server farm. And guess what? We're going to run out of that, so we have to find a way to expand and extend that capacity. But of course, engine test data is full of export control and intellectual property. So I can't just put it on an Amazon cloud server and hope that it's there when I want it in a year's time. I've got to put it somewhere that I can have some control over. And I can't just access it by opening a file and looking at it going, there's the test results, because it's a stream of thousands of parameters taken tens or hundreds of times a second associated to engine control parameters like throttle and pressure and temperature that are all varying dynamically. So my mapping and understanding all that testbed data is remarkably hard. So I find myself with engineers, guess what, writing code to do it. So I'm back at the same place every single time. If I don't enable my engineers to write this code, they will always come up with demand signals, use cases, faster than the vendors and my IT organization can keep up. So I need to find a way to deal with that problem. And the only way I can see to deal with it is no-code, low-code stuff. And that's why when I joined in 1990, there were people writing it in Fortran. And I'm sure when I retire at some point in the next few years, there'll be people writing it in Mendix, maybe. No-code, low-code tools, because that's the point. And I popped this one in just as a chart to close with. Because I mentioned about factories and supply chains and I skipped over it, so I better come back to it. So about 80% of a jet engine we don't make. There's about 20% we do make, and it's very precious to us, and we control it. And it's in our factories, and they are progressively all moved onto somatic and then op center platforms if you're in aerospace and defense. So we can gather all the information we want to. There are some niggles about that. If I go into some of our shop floors, some of the machinery is quite old, because the flow rate through the factory means the capital investment process doesn't work if you're going to write off the factory and rebuild it every 2 or 3 years with every new product. So we've got some kit that's very old. We've got some factories that are inside are very old. The outside might be a brand new shiny building, but inside it's still quite some of the old kit. And we have to use it. We have to use it because we couldn't afford to replace it because of the capital question, but also because there's lots of know-how and IP locked into that factory configuration. We want to model it, so we're doing some work with our colleagues in Siemens about how we model that and keep track of it and manage it and extend it onto new factories. But fundamentally, we've got an industrial footprint that's fairly old school, a variety of machines on it generating data, and we're feeding it back into that cloud. And that's fantastic for 20% of the bits. I can actually cope with that. My dilemma is the rest of it's bought from outside. Some of it's bought from companies bigger than us. Some of it's bought from a company that's literally an industrial unit in a small industrial town in Birmingham or in Indiana or in former East Germany near Berlin or in Hungary. Some of it's a production part, some of it's a prototype part. All of it's got richness locked up in how it was made in its manufacturing data. Because all those factories are just like mine. They're full of machines of varying ages with varying types of data collection. They could collect more data if I could tell them what to collect. But even if I do, they can't give me it back. They can't give me it back because to get it onto my estate, they have to get through my IP export control security arrangement. If I'm a company bigger than Rolls Royce based in the USA, I might not want to do that because that opens a doorway between the two companies and my secrets might leak out. So I have an argument there. If I'm a small factory somewhere in Birmingham or Indiana or wherever, and I've literally got a machine tool in a room, I can't afford the IT infrastructure to do that the way the MOD or the DOD would approve. I need to find a way to help the people in that grey box talk to me about what they're doing. So I need the industry to create, wouldn't it be nice if there was sort of an app store, citizen coding thing that businesses that enter the marketplace that offer me the ability to make parts could also rock up and relatively cheaply and simply with their own employees construct tools to capture and share the data that they're creating in the factory about the parts they're making for me without giving away anyone else's secrets, because I don't want anyone else's secrets. I just want to know about the part you made for me. So it was fascinating the other day. We had a call on Friday with, and I'm not sure I left them overwhelmingly reassured about what I was going to say, because I didn't really know on Friday. I had a call on Friday with the Mendix and Siemens team about what I was going to talk about and showed them these slides. And I said, what do you want me to end saying? And he said, well, can you sort of say that Mendix is like nice, to paraphrase it? Right. Well, yeah, I think I can. I'm going to qualify that. I don't know. I don't know yet, because I've not tried to fix these problems with it yet. What I can tell you is all the problems that were described in that previous presentation, if you don't already know because of the companies you work in, can I just reassure you they really are very, very real for the aerospace, defence and nuclear industries, because that's what my business does. And if I nip across to Germany and visit my colleagues in Rolls Royce Power Systems, who joined us from being owned by MTU Daimler, who make diesel engines for trains and tanks and boats, and microgrids and fuel cells and all sorts of fun stuff, they have just the same set of issues that we do in the aerospace and defence side, even though they grew up in a completely different country, under completely different ownership, with different IT people and different engineering systems and different engineers, same problems. And when we bought the Allison Engine Company joined our group in the mid-90s, and turned up with their estate, it all looks the same, it all feels the same. So I can really, really reassure you that the problem statement described is correct. I can really, really reassure you that listening to the way that Mendix is going to try and fix that problem statement feels good to me. Feels like it should help. The proof of the pudding is going to be in eating, and a few of my colleagues are here, and you might bump into them as you walk around the room. Feel free to chat to them. They know what they're allowed to talk about and not, I hope. Pretty sure they do. They're trying to cure some of these problems. So I guess I'll stop at that point, because I've rambled from the allocated 30 minutes, and I am notorious for talking far too much. But yeah, thanks for the opportunity. I'm looking forward to the rest of the day. Our host.
Thanks, Dave.